Welcome, everybody. It's my pleasure to introduce Shu Kanazawa, who today will be telling us about a limit theorem for Betti numbers of homogeneous and spatially independent random simplicial complexes. Thank you.
Thank you, Henry, for the introduction, and thank you, organizers, for giving me an opportunity to speak here. So today, I'm going to talk about Betti numbers of random simplicial complex, which has drawn attention as a higher dimensional generalization of random graphs. This study was supported by JSPS Kakenshi grant. So before the main part of my talk, let me explain the basic thought behind of my work and by the setting of random graphs, especially the Erdős graph model. So first, Kn is the complete graph on n vertex set from 1 to n. And the Erdős graph, denoted by GNP, is defined as a random subgraph of Kn with all vertices, where each possible edge appears independently with a probability p. As you can see from the picture below, the number of connected components of Erdős graph decreases with respect to p. Then, how does the number of connected components decrease? Erdős and Rényi have answered this question in 1960s. They showed the following. Let GNP be an Erdős graph with P equal to C over N for some positive constant C. Then the number of connected components of GNP divided by N converges to some constant depending on C in probability as N goes to infinity. So as you can see from this graph, the limiting constant is monotonically decreasing with respect to C. So the basic thought of my work is the quest for higher dimensional analogs of this theorem in the setting of random simplicial complexes. So before the main part of my talk, here is just a quick outline. We start by introducing some random simplicial complex models and discuss the asymptotic behavior of their Betti numbers. Then I will state our result and give an outline of the proof. Once we understand our approach, we can go through further generalized results. Okay, so one of the typical random simplicial complex models is the linear Meshulam complex model. Triangle N is a complete simplicial complex on n vertex set, which has all possible simplices. And let D be fixed as a natural number. Then the D linear Meshulam complex denoted by YD and P is defined as a random subcomplex of the complete simplicial complex, which has all possible D-1 dimensional simplices, and where each possible D-dimensional simplex appears independently with a probability P. Here is just an illustration for D equal to 2, but imaginably, the D minus first Betti number decreases with respect to P because D-1 dimensional cycles are gradually field by with these simplices. So how does the d minus first Betti number decrease? Linial and Peled answered this question, and they showed the following. Let YD and P be a linear Meshulam complex with P equal to C over N. Then the normalized d minus first Betti number converges to some positive constant, some constant depending on D and C in probability as N goes to infinity. So as you can see from this graph, the limiting constant is monotonically decreasing with respect to C, which reflects that the Betti number of linear Meshulam complex is monotonic. So, but actually, in the case of most of random simplicial complex models, the Betti number behaves non-monotonically. To see that, let me consider another model called random clique complex model. So the random clique complex denoted by C and P is defined as the clique complex of the Erdős-Rényi graph G and P. Let me explain a little more about the definition by the picture below. So here is just a sample of Erdős-Rényi graph. And the clique complex is constructed as follows. If we have this 3-vertex clique, then we put 2 simplex on it. And if we have this 4-vertex clique, then we put 3 simplex on it. And we repeat this process for 5-vertex clique and so on. Then we obtain a sample of a random clique complex. So what I'd like to remark here is that the Betti number is no longer monotonic. As you can see from this numerical experiment, each dimensional Betti number behaves almost unimodal, except in the case of 0-dimensional, corresponding this blue line. So this unimodality comes from the competitive relationship between the effect of creating cycles and that of filling them. For instance, back to the left slide, left picture, this blue line creates a cycle, but this red line breaks that cycle because of the definition of a clique complex. So here my question is, can we prove a limit theorem for Betti numbers which reflects such unimodality? Okay, so let's move on to our result and the outline of the proof. So we showed the unimodality problem. So let C and P be a random clique complex with this parameter setting. Then for any K, the appropriately normalized Betti number, case Betti number, converges to this constant in probability as n goes to infinity. So as you can see from this graph, the limiting constant behaves unimodally with respect to C, which consists with the previous numerical experiment. So the proof is similar to the case of linear Meshulam complex, except that we must consider both effects of creating cycles and that of filling them this time. Furthermore, the appearance of each simplex is not stochastically independent this time, which complicates the situation. So anyway, the important thing for the proof is the following local weak limit theorem. Roughly speaking, the theorem says the following. Under this parameter setting, the random Lie complex C and P converges locally weakly to random higher dimensional tree in probability. I'll explain the key point rather than detail by the illustration for k equal to 1. For each fixed one simplex, there are binomial number of two simplices containing it. And from the setting of parameter P, this binomial distribution can be approximated by the Poisson distribution. And this process continues again and again. So then the Poisson branching higher dimensional random tree comes up as a limiting object. For the last part, for the proof, we must read off the asymptotic behavior of Betti numbers from the local weak convergence result. This is some kind of systematic way. If you're interested in details, please check the paper by Rényi and Peled or my current archive preprint. Okay, so far we have seen the linear Meshulam complex and the random Lie complex models and discussed the asymptotic behavior of their Betti numbers. Once we establish our approach for the proof, it turns out that the approach is also valid for larger framework. So whenever the random simplicial complex satisfies just two properties, one is homogeneity, and the other one is spatial independence. So first, let me explain a little more about these two properties. First, let Xn be a random subcomplex of the complete simplicial complex. Then Xn is said to be homogeneous if Xn is invariant in law under any permutations on n vertex set. Roughly speaking, which says that all vertices are equal in a sense. Next, Xn is said to be spatially independent if for any subcomplex y1 and y2, and the events that y1 is contained in Xn and that y2 is contained in Xn are stochastically independent condition on this event. The important thing here is that previous three models satisfy these two properties, and the approach for the proof is also valid in this larger framework. Then I will show this result. This is main result, and this is the last slide of this talk. So let Xn satisfy homogeneity and spatial independence, and let K be fixed as the dimension we consider. Sorry. And using a K simplex tau and the K plus 1 simplex sigma containing tau, we define two important parameters, Qk and Rk. Qk is the probability that tau appears in Xn, and Rk is the probability that sigma appears in Xn given tau appearing in Xn. So then, if the Qk and the Rk satisfy this parameter setting, then the normalized case Betti number converges to this constant in probability, which can be regarded as the law of large number for Betti number. And the previous result on linear Meshulam complex and random Cleve complex model is obtained by this theorem as a special case. So at the very end of my talk, let me summarize my today's talk. So first, I talked the asymptotic unimodality program of Betti number of random Cleve complex. And for the proof, the notion of local weak convergence for simplicial complexes is crucial. And we pointed out these two properties, homogeneity and spatial independence, is a key for the proof. And lastly, we stated the law of large numbers for Betti numbers. Okay, this is all for my talk, and so thank you for your attention. Thank you for your attention.
Thank you very much, Shu. That was very nice. So before we get to questions, if everybody could briefly unmute yourselves, and then we'll clap, and then we'll mute ourselves again. Questions for the speaker? Let me start with the first question. So, Shu, I was curious, what is known about the limiting function HK? So you know that it's unimodular, is that right?
Yes.
Do you sort of know, do you have any guesses at the formula for it, or
I'm sorry,
do you know more about it besides it being unimodular? Like, do you know what the function?
Yeah, we have explicit formula for HKC.
Oh, wow.
And this peak corresponds to K. So this is K equal 1. Yeah, anyway, the explicit formula is known.
Wow, what's involved in the explicit formula? And is it piecewise, like between 2 and 3? There's that vertical line. You know, is the function defined in a piecewise fashion?
Sorry, I didn't understand your question. Could you?
Oh, I guess
yeah.
I guess roughly what shows up in the formula, the explicit formula, like exponentials or.
This formula is expressed by a solution of complicated formula. So
sure.
I'm sorry.
That's very nice. That's impressive.
Yeah, if you're interested in, please see this. I could preprint for the explicit formula. Yeah.
Will do. Other questions for the speaker?
I do have one. I don't remember exactly this the slide number, maybe 5 or 6.
Mm-hmm.
If you could go back to those.
No, 5 or 6.
All right, sorry, can we go ahead maybe 2 more? Yeah, this one. Thank you.
This slide. Yeah.
So, yeah, I was just trying to make sure I properly understood the definition of the random clique complex. So, in this case, in the diagram on the left-hand side, the upper part, the shading there is a 4 simplex. Is that correct? It's actually the or I'm sorry, I guess that's a 3 simplex. I'm sorry, but so it's different, right? The triangle on the bottom is just a 2-dimensional shading, right? But the shape up above is a tetrahedron. Is that correct?
Yes. So solid tetrahedron, and this is solid triangle.
Okay, I see.
Yeah.
So simplices of arbitrary higher dimension can appear, and that's the whole point. That's actually the right. Obviously, the larger ones appear with much lower probability. Okay.
Yeah.
Thanks.
Yes.
Other questions? So Shu, I had another question for you. So what is a higher dimensional tree for you? I've seen one paper by Gil Kalai where a higher dimensional tree is a simplicial complex where the lower dimensional homology vanishes, but then homology appears in one dimension. I guess he's using rational coefficients. Is that related to what your higher dimensional tree is?
And those are different. So actually, I didn't understand much about it, but this is different one by Clive, higher dimensional tree.
And then omega 1 on your last slide or second to last slide.
Omega.
Keep going.
Omega.
Yeah. Omega 1. What does that mean?
This left-hand side converges to infinity as m goes to infinity.
I see.
Yeah.
Further questions for Shu? Wonderful. Well, if not, thank you again for a beautiful talk.
Thank you very much.